Now let's take a look at Lewis formula of molecules. And what Lewis formulas allow us to do is they show a pattern of valence electron distribution in the molecule. This is useful for understanding the bonding in many compounds. It allows us to predict the shape of molecules, and this in turn allows us to predict the properties of molecules and how they will interact together. Now, this slide here you'll want to remember and maybe come back to again and again or take notes on this, because here are some common bonding patterns that are going to help you recognize whether your final answer makes sense or not. The element carbon in a molecule is always going to have 4 bonds. And no lone pairs, at least in this chemistry class. So those 4 bonds can either be 4 single bonds, or 2 double bonds, or a single bond and a triple bond, or 2 single and 1 double. But however you add it up, carbon will always have 4 bonds. Nitrogen in this class is going to have 3 bonds and 1 lone pair. So here's our carbon, here it is with 4 single, but it can really have any combination of single, double, and triple as long as there's 4. Here's nitrogen, 3 single bonds and 1 lone pair. Oxygen, 2 bonds and 2 lone pairs. Oxygen can also do a double bond, but again that will still just be 2 bonds and 2 lone pairs. Hydrogen and halogens are going to have 1 bond, and then boron is an exception to the octet rule. It's going to have 3 bonds, so it only has 6 electrons around it, and no lone pairs. And then beryllium, even though it is a metal, here it is right here, it doesn't have as much metallic character as some of the other elements. So therefore, it does undergo bonding very similar to covalent bonding by sharing electrons. So beryllium will have 2 bonds and 0 lone pairs. So here we have some exceptions to the octet rule. Beryllium will have a total of 4 electrons around it, and boron will have a total of 6. Nitrogen, oxygen, and the halogen and carbon are all going to have 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And of course hydrogen can only have 2 electrons. So it's always going to be an exception to the octet rule. Now, to give you an idea of what we're going to be looking at, this is an example of a Lewis structure for a molecule. Anytime electrons are being shared, they're drawn as lines, and these dots here represent the lone pair electron. And if we look at the atoms in this molecule, each atom has 8 electrons around it. None of these are exceptions to the octet rule. So let's look at where we need to start to come up with a structure like this. The first thing that we're going to do is we're going to attach the atoms together in a skeletal structure. And when we attach them together, we're going to put them together with single lines which indicate a single bond. Now, to do this, we've got to know how they're going to be attached. The most metallic element, or the largest element, is generally going to be the central one. However, if you have a molecule like this, phosphorus trichloride, there's only 1 phosphorus. If there's only 1 of an element and more than 1 of another element, the one there's only 1 of is going to be the central atom. Halogens and hydrogens are generally terminal, meaning they only have 1 bond and are not going to be the center. So in this has a special name because it's organic, but let me just call this dicarbon tetrachloride. The carbons are going to be attached to each other, and the chlorines are going to surround them right here. And the way you would figure that out is chlorines can only have 1 bond. Halogens are only going to have 1 bond, so they can't bond with one another in something else. Many molecules tend to be symmetric. So here we have a symmetric molecule, 2 carbons, and 2 chlorines on each carbon. Now here's something important. In oxyacids, the acidic hydrogens are attached to an oxygen. So in H2SO4, we have 1 sulfur. That's going to be central. The oxygens are attached to the sulfur, and each hydrogen is attached to a different oxygen. Okay, so step 1, attach the atoms together in a skeletal structure. Step 2, calculate the total number of valence electrons you have. These are the electrons that do the bonding and that act as lone pairs as well. To do that, use the group number on the periodic table to find the number of valence electrons for each atom. So as a reminder, this family has 1 valence electron, this has 2, 3, 4, 5, 6, 7, 8, except for helium. Now if we're looking at a polyatomic ion, for a cation, it means we've lost an electron. So we're going to subtract 1 electron for every positive charge we have. And if we have an anion, we're going to add an electron for every negative charge that we have. So we have to deal with this if we have polyatomic ions. Then we have to account for our electrons. We'll take a look at how to do this, and then we see how many electrons we used in bonding, and however many electrons we have left, we want to distribute so to complete the octet of all atoms. Now, we want to remember that hydrogen only wants 2, boron is okay with 6, beryllium is okay with 4. And at this point, if there's not enough electrons to complete the octet, then we want to share more by using double or triple bonds. And we want to try and follow the common bonding patterns. That's going to help us figure out if we're on the right track or not. Okay, so I'm going to stop this right here. We've gone over the rules, and then our next voice lecture will be going through some examples.